Hey, welcome back. We've got an interesting problem. So it's a combined loading problem, and again, we're advancing it to try to add a little bit of complexity, a little bit of interest to the problem. And so in this case, we have a round circular shaft coming out from a fixed support, and we're putting a whole bunch of loads on it. So we have take note of the axes. So we have the x-axis, horizontal. I guess left and right. left. That's why we drew it out in 3 dimensions. So we have the x, y, and z axis shown on the diagram. So take note of those because we're going to be referring to them all the way through the problem. So we have forces acting in the x, y, and z directions, all at the end of the rod. We also have a torque of 9 kilonewton meters about the z-axis at the end of the rod. But what we're going to do is figure out what the stress conditions are at points A and B. Points A and B, 2 different positions at the cross-section right next to the support itself. So we're going to figure out what all these forces what they're contributing to forces at the cross-section AB. Then we're going to figure out what stress contributions each of those have on that at points A and points B. Add them all together because we're going to use superposition to figure out what the net stress condition is at points A and B. So I've got the problem sheet kind of laid out because I don't want to waste a lot of time with drawing pictures and stuff like that. So we're going to start across the top here. We're going to do that, and then we'll move on from there. So contributions at the cross-section AB. So I need to look at each of these forces, and I have to figure out what contribution they're making at the cross-section AB, effectively moving them to the centroid at AB and adding any additional contribution that they might be making. So we're just going to work through them one at a time. So we're going to look at the 400 kilonewtons that's acting in the positive Z direction. And so I'll label that here. So 400 kilonewton force, and the contributions, it's basically a normal force at the centroid at cross-section AB equal to 400 kilonewtons. And we don't have to add anything else. It doesn't contribute a moment, doesn't contribute a shear or anything else, just the normal force of 400 kilonewtons. Then we will look at the 8 kilonewtons going in the negative Z direction, so the 8 kilonewton force. And when I consider what it does at the cross-section AB, the obvious one is that it provides a shear force of 8 kilonewtons, and that's going in the negative X direction. And it also provides bending about an axis at the AB, right? Because we have that moment arm, perpendicular distance, if you will, from that plane to this plane of 0.75 meters or 750 millimeters. So it would cause bending, and in this case, if I look at that, that would be bending about the y-axis, bending about y. And if I want to know what that value is, so m sub y is equal to our 8 kilonewtons multiplied by the perpendicular distance, which is 0.75 meters. And that's equal to 6 kilonewton meters. Oh, I thought I was going to run out of space there. And so that's the only contributions the 8 kilonewtons make. So let's look at the 10 kilonewton force. And of course, it's going to provide a shear contribution of 10 kilonewtons. And it's going to be going in the positive y direction. Then it also provides bending, right? Because it's displaced that 0.75 meters from that cross section. So when we look at what it does though, so it goes and it does bending about the x-axis, right? Trying to bend this shaft down. And so that would be a moment about the x equal to our 10 kilonewtons multiplied by our 0.75 meters, and gives us a 7.5 kilonewton meters for bending about the x. And finally, we have our torque of 9 kilonewton meters, and that just provides a torque about the z equal to its value of 9 kilonewton meters. So what I want to do then is to transfer all of these to our cross section. So that's why I've drawn this diagram here to the left. And so I'm just going to work top to bottom, and I'm going to draw them in. So we have our 400 kilonewtons going along the z-axis, right? That's our normal force. That's 400 kilonewtons. And then our 8 kilonewtons we said was in the negative x direction, so we should have an 8 kilonewtons there. And then it has bending about the y-axis, so we want to be bending about the y-axis equals to 6 kilonewton meters. Now if I look at the 8 kilonewton meters, it's trying to bend this shaft away from me, so it's going to be causing compression at B. So this is a negative y, so I'm going to draw that torque in here. And label that as, what did we say it was, 6 kilonewton meters. And then we have our 10 kilonewtons. And so it's acting down. And it's causing bending about the x-axis, so it'll be along the x-axis. Now, we already said that it's bending it down, so it's causing compression along the bottom. So when I draw this in, I should be drawing that moment about here, so that using the right-hand rule, it's causing compression on the bottom. And we said that was 7.5 kilonewton meters. And then finally we had a torque about the z, so that's on the z-axis. It's positive in the z direction. So we have our torque. And that was equal to 9 kilonewton meters. And so all we need to do is, so we have three forces, three moments, if you will, is we have to apply those with the appropriate equation to get the stress, the appropriate stress that they're causing at our points A and B. And remember, I'll draw them in here. So remember, our point A is up here, and our point B is down there. So I'm happy there. We have all of our forces acting on the cross section. So now we need to calculate those stresses. So to get there, we need the section properties. I didn't want to waste a lot of your time doing the section properties, so I went ahead and calculated those. That's why they're down here. So we have the area of the cross section, area of a circle. We have the moment of inertia about either the x or the y-axis. It's symmetric that way, so they would be the same. So our I value, then we have our polar moment of inertia, J, calculated out here. And finally, we have our Q at the neutral axis. And it's the only one we're going to need, so we went ahead and did that. So if you're not too familiar with the circle, so we have half the area, that's easy enough, multiply by the distance from the neutral axis to the centroid of that area, and that's shown here as 4r over 3 pi, and so that's how we calculate Q. So with our section properties all done, we're now ready to apply all of our stress formulae to figure out the stress components that they're adding to points A and points B. So the way I normally do this is I go through and I do the normal forces or the normal stresses first. So those components which are adding to normal stress, I do that first. And then we'll deal with the shear stresses. So we'll look at axial. And of course, axial would be a sigma z, and it would be equal to a force divided by our area. And so that force, which is causing an axial force on this, is the 400 kilonewton force in the z direction. And so we have our 400,000 newtons divided by our area, which we calculated as 7,854 millimeters squared. And we get a stress of 50.93 megapascals. And that's going to be in tension. And recall that will be equal across the entire cross-section. So it's going to be 50.93 megapascals in tension at both A and B. So at A and B. So then we're going to do our bending about X. And so that again would be a normal stress in the Z direction, and that's equal to our moment in X multiplied our distance in Y divided by our IX. And of course our IX, our IY, we already said are going to be equal to each other. And so in this case, our moment in X is equal to our 7.5 kilonewton meters. So we have 7.5 times 10 to the 6 Newton millimeters. And our distance Y is the radius, or 50 millimeters, divided by our I, which we already calculated to be 4.909 times 10 to the 6 millimeters to the 4th. And that gets us a value of 76.39 megapascals. Now, that's at the extreme fiber, bending about the x-axis. So A is at the extreme fiber. And when we look at the direction, using my right-hand rule, it's going to be compression at the bottom, tension at the top. So we're going to say tension at A. And B is actually on the neutral axis, which is the x-axis. So it's going to be 0 at B. So it's not actually going to affect the stress condition at B. So now we're going to do the same thing, bending in the y-axis, or about the y-axis. And sigma z, it'll cause a normal stress in the z direction. And that's equal to our my times our distance x, iy. And so this moment then is equal to our 6 kilonewton meters, or our 6.0 times 10 to the 6 Newton millimeters. Again, our x direction is our radius of 50 millimeters, and our I is the same, 4.909 times 10 to the 6 millimeters to the 4th. And this is equal to a value of 61.11 megapascals. Now, as I look at it, so it's going to be causing compression. It's pushing this rod away from me. So it's going to be causing compression at B. So let's say, and the neutral axis is the y-axis, so it's going to be 0 at A, because A is on the neutral axis, and compression at B. So that's it for normal stresses. The rest are all going to be shear stresses. So I'm just going to note that those are the totality of my normal stresses. And now we'll look at shear stresses. So we're going to do shear in Y. And so these are transverse shear stresses resulting from bending. That's that shear, that V on the cross section itself. So our formula then is tau is equal to VQ over IT. And so our shear force in the Y direction is our 10 kilonewtons, or our 10,000 newtons. And our Q we calculated is 83.33 times 10 to the third millimeters cubed, all divided by our I, 4.909 times 10 to the 6 millimeters to the fourth, times our thickness, which is the diameter, right, across that neutral axis. So it's the full diameter of the cross section, which is 100 millimeters. And so that gives us a value of 1.69 megapascals. So that's as a result of the 10 kilonewtons going down. So keep in mind that that's the bending about the x-axis. So the transverse shear stresses, remember, maximum at the extreme fibers, maximum at the neutral axis, which is the x-axis in this case, and 0 at the extreme fibers. So at A, I would expect this to be 0 at A, which is the extreme fiber, and a maximum on the neutral axis, which is at B. And so it's going to be at B, and it will take its direction from the 10 kilonewtons, which would be positive Y, I guess, positive Y or down, positive Y, which is down in this case at B. So we do that one more time, and we have another force causing shear, and that's in the negative x. Okay, so in the x, so tau equals VQ over IT, 8 kilonewtons. I'm reading that wrong. So 8,000 newtons. Q is the same, 83.33 times 10 to the third millimeters cubed. I is the same, 4.909 times 10 to the sixth millimeters to the fourth, and our diameter of 100 millimeters is our thickness, and that's equal to 1.35 megapascals. So this is the 8 kilonewtons going off in that negative x direction, which is in conjunction with that bending about the y-axis. So again, if we think of our transverse shear stresses, they're going to be maximum at the extreme fibers, which would be at B, and 0 on, stated that wrong, we are going to be maximum at the neutral axis, which is the y-axis in this case, so at A, and 0 at the extreme fibers, which would be at point B. So what do we have here? So we go, it's negative x or right at A, and 0 at B, because it's on at the extreme fiber. And so finally, the last shear stress is shear stress due to torsion. So shear about Z, and so that shear stress is equal to TR over J. That's, our torque is 9 kilonewton meters, or 9 times 10 to the 6 newton millimeters, times our radius, which was 50 millimeters, and our polar moment of inertia on the bottom, 9.817 times 10 to the 6 millimeters to the fourth, and that gives us a shear stress of 45.85 megapascals. And so that's going around the cross section counterclockwise using my right hand rule. And so that's going to be up at B, which is negative y. And it's going to be left at A, which is positive x. And those are all the stresses that are being caused at our points. And so what I need to do is I need to add up like stresses in like directions and put them on our cross section. And so what do we have here? So if I look at A and I add up all our normal stresses, so I have 50.93 megapascals in tension at both A and B. I have 76.39 megapascals tension at A, and the other one is 0 at A. So if I add those two values together, they're both tension, so let's show that as tension. All right, my straight line not doing so well, but we add those together and we get 127.32 megapascals. And I'm going to do my normal stresses at B, and so we have the 50.93 megapascals tension due to the axial load, and the next one is the 61.11 megapascals compression at B due to bending about the Y. So we have to do the 61.11, subtract the 50.93, and that gives us a value of 10.18 in compression. So at B, I'll have to draw it the other direction. So I'll put my arrowhead there, and we get a value of 10.18 megapascals. So now we have to do our shear stresses, and so I'm just going to work my way down. So at A, we have the first one is 0, so it doesn't matter. So we get a negative 1.35, sorry, negative x direction 1.35, and that's at A, and then it's going the opposite direction, positive x direction, 45.85. So we're going to have the 45.85 less the 1.35. So we have a shear stress going in this direction, and it's going to have a value of 44.48 megapascals, which was the 45.85 less the 1.35. And then at B, we have down 1.69 or positive y. This next one is not, it's 0 at B. And then finally we have the 45.85 is acting up at B. So we have to 45.85 subtract the 1.69, and that leaves us with 44.14. 44.14 megapascals acting up at B. And that's it. So now typically what would come next is we would take these stresses and we would apply them to our stress element and do our principal stresses or some other evaluation based on it. But this is where we're going to stop on this question, and hopefully that was helpful. They are complicated. They do take a lot of thinking. You have to visualize it, and you may have to come back and redo this 2 or 3 times in order to really see the process as we work our way through it. But hopefully that was helpful, and you're able to figure that all out.